Okay, welcome everybody to lecture number 16. So our theme today is the completeness axiom for the real numbers. And we've had a break of last week since the last time we met. And let's just recall briefly, although we don't directly need it for today, what we've been talking about. So essentially the last 3 or 4 lectures, I suppose, we've been talking about the concept of cardinality for infinite sets of real numbers and the notion of countability and of uncountable sets of real numbers. And we saw, for example, that the set of rational numbers is a countable set in that it can be put in bijective correspondence with the set of natural numbers, 1, 2, 3, etc. The set of integers also is countable. And we saw in our last lecture or two that the set of real numbers itself is not countable. And we did that by using this famous diagonal argument of Cantor, which shows that even the real numbers in the interval from 0 to 1 can't be put in bijective correspondence with the set of natural numbers. They can't be organized into a list. There are basically just too many of them. They can't be accommodated in a list that has a first element, a second element, a third element, a fourth element, and so on. No matter how you try to organize them into a list, it can't be done. Your list will always be missing some elements. So that, as we saw, is sort of a classical and very famous discovery of late 19th or early 20th century mathematics, which really did have a massive influence on the development of the subject since then. And so we're not really going to talk so much about that in this section. So in a sense, like you don't have to have a direct close recall of all the stuff we've been talking about countability. But we're going to talk about something else, something slightly different from that, which is the so-called completeness axiom in the real numbers. And so basically in this section, we're going to be talking about bounded subsets. And we're going to be talking about an important distinction between the set of rational numbers and the set of real numbers. And I have to sort of confess in advance, like many things in this subject, I think this distinction, when we highlight it, it's going to look like really kind of making a big fuss about a really small point. And I think it takes a little bit of time and practice and kind of working with these ideas to kind of get a strong sense of why this distinction is really important, because it can appear as a sort of a bit of pedantry when you first see it, that we're really sort of making a big song and dance about something that's a little detail, but it's a detail that turns out to really capture an essential difference between the set of real numbers and the set of rational numbers. So we're going to look at a few kind of specific examples to get a handle on this and see what we're talking about. Essentially, what we're going to be talking about is the concept of a greatest element or maximum element in a set, and another concept closely related to that called the supremum, which is close but not the same thing. Okay, so a bit of background. What have we seen so far about the rational and real numbers? Well, we see that the set of rational numbers is countable and the set of real numbers is not. And that's an important distinction between these two sets, that their cardinalities essentially are sort of different magnitudes of infinity. So in that sense, there are many more real numbers than rational numbers. But in another sense, the rational numbers are the numbers that we work with in sort of practical ways, and they can approximate real numbers as closely as we could possibly want. So the set of rational numbers is dense in the real numbers. And that means when you look at the real number line and sort of highlight all the points that represent rational numbers, they're densely crammed in there. There are no gaps. There, no matter where you are in the real line, there are loads and loads of rational numbers as near to you as you could want. So this statement has a practical impact, which we use absolutely all the time, doing any kind of quantitative work, and even sort of in probably everyday life as well, which is that every real number, whether it's rational or not, can be approximated by a rational number with as high a level of accuracy as we like. So in practical terms, when we're doing calculations, when we're working with quantities of things that we might want to measure or whatever, when you're, no matter what the context is, whether it's something in the natural or physical sciences, or whether it's in economics or sort of everyday life, whether it's looking at the COVID numbers, you're using rational numbers all the time. And so what do we mean by saying that any real number can be approximated with a level of accuracy as high as we like by a rational number? Well, suppose we take the irrational number pi, which is a real number, but not rational. And so pi is 3.1 something. So 3 is a rational number, which is an approximation for pi, not a great one, but it's the nearest integer to pi. Okay, 3.1 is a rational number. It's 31 over 100. It's a better rational approximation for pi than 3 is, but it's still not equal to pi. 3.14, again, that's 314 over 1,000, so it's a rational number. That's a better approximation again to pi than 3.1 is, and so on. So you can keep, you can keep truncating the decimal approximation of pi after successive digits, and what you get are better and better rational approximations to pi. And so, like, if you want a rational number that's within 10 to the minus 20 of pi, you can take the first 20 places after the decimal point in the decimal representation of pi, and you can truncate it there. What you have is a rational number. It's not equal to pi, but it differs from pi by no more than whatever, 10 to the minus 20 or whatever, a tiny, tiny number. So that's kind of what's meant by this statement, a level of accuracy as high as we could want in the statement of the lemma, which says every real number can be approximated as closely as you could want by a rational number. Okay, so a sort of practical, I suppose, conceptualization of that statement is to just think about decimal approximations or decimal representations truncated at some point. Those things are all rational numbers because they're terminating decimals, and they, by terminating far enough out, you can get the level of accuracy as high as you like. Okay, so, and when we work with computers, so I'm going to say something here that is, if you're a computer scientist, I'll ask you to just kind of not analyze this too deeply, the statement that I'm going to make, because it's not completely true. But the fact that all real numbers can be approximated with arbitrary closeness by rational numbers is used all the time. And computers, basically don't deal with all real numbers. They don't deal with decimal representations that are infinite non-repeating strings. They truncate somewhere and they work at some specified level of precision. So even that statement is not completely true, as people who studied floating point arithmetic might know. But basically, computers work with some subset of the rational numbers when they're calculating things. And calculators the same. They don't really work with all the real numbers, which mathematicians fuss about. So what are we talking about when we talk about the distinction between real and rational numbers, when we try to prove theorems about real numbers? Remark here is that rational numbers are the numbers that we use for practical purposes. And even when you're doing computational work, probably you're only working with some subset of the rational numbers. You're not really working even with all the rational numbers. You're working at some specified level of precision, probably, more or less. Okay, second remark here, the sequence of truncated decimal representations of pi, that's a sequence, and we're going to have a formal meaning of sequence in chapter 3, but it just means like an infinite list of numbers. So the sequence here, whose first term is 3, second term is 3.1, and so on, that's a list of numbers that are, okay, the word steadily here, you could ask for a formal definition of that, and I'm not going to give one, but it's a list of numbers that's approaching pi. Its members, the terms in that list are getting nearer to pi. Okay, there's no term in the list that's actually equal to pi, because every term is a rational number. Every term there is a truncated decimal, but the further out you go, the nearer to pi you get, and you can get as far as you want to pi, as near as you want to pi, by traveling far enough out along this list. Okay, so we'd say that sequence converges to pi, and I suppose here the thing I'd kind of suggest giving attention to is the fact that every term in that sequence is a rational number. Okay, but the thing that they're approaching is not a rational number. So we can have this idea of irrational numbers like pi sort of occurring as kind of limits of sequences of rational numbers. And that's a really important sort of notion with the real numbers. The real numbers include things that aren't rational, but they have sequences of rational numbers kind of converging to them in this way. We'll be making this more precise in the next couple of lectures. Okay, so that's sort of a thought to have carrying around with you when we're talking about this stuff, that you can have, by taking some irrational number, that means a number with a decimal representation that isn't regular, that doesn't terminate, that doesn't repeat. You can kind of take this, associated to that, you have this sequence of rational numbers, which is approaching that irrational thing. Okay, the title of the section is Completeness for the real numbers. So we haven't seen the word completeness yet, but we're coming to it. Okay, and the third remark, just in case you're kind of wondering about this, which would be very reasonable, we haven't looked at all yet at the question of, how we know these decimal approximations to pi. How can we get our hands on better approximations to the value of the irrational number pi? So like, I'm claiming that they exist because you can truncate this decimal representation wherever you want, but how do you actually calculate the digits of this decimal representation? We haven't talked about that, and it's a completely different question. And it's also a very interesting one, but it's something that we look at in chapter 3 a bit. I suppose if you believe that pi has a decimal representation, then this idea that you can truncate it at successive points to get a sequence of rational numbers that approaches pi is plausible. Whether you should believe that this is actually the first, 7 or 8 digits of the decimal representation of pi is something that you should, that you can take my word for if you want to, but we will see some ways of actually computing those digits in chapter 3. Okay, that's kind of by way of sort of ideas that feed into this topic of completeness. And the main one, I guess, is this idea that you can have a sequence of rational numbers whose terms are approaching something, and the something that they're approaching need not necessarily itself be rational. Okay, if anybody has a question, please feel free to ask one. I'll pause for a second, just in case anyone does. Okay, if not, then let's recall this concept of upper and lower bounds. So our context now is we're talking again about subsets of the real numbers, and we're going to try to pinpoint an essential property of bounded subsets of the real numbers that isn't shared by bounded subsets of the integers or the rational numbers, particularly the rational numbers. Okay, so we need a couple of definitions, and this is something that we saw before, but let's recall it. So suppose we have a subset of the real numbers. Okay, this looks like a very kind of formal thing, but hopefully it isn't so bad when you think about it in practical terms. So we've got a subset of the real numbers. So here's the real number line. And an element B, a real number B, is called an upper bound. So there's a real number B. It's an upper bound for the subset S if every element of X is at most equal to B. So I'm going to draw the elements of S in green. So maybe they're spread out, maybe they're scattered around like this. Maybe they include some intervals. So maybe there are some kind of chunks that are all colored green. Maybe B is there. Maybe there are some elements to the left of B that are there. So the subset, let's say the subset S consists of the points that are labeled green here. So to say that an element B of R is an upper bound for S means that X is less than or equal to B for every X in S. So all the green points basically are not to the right of B. So, okay, so X less than or equal to B, of course, means that X could be equal to B or it could be to the left of B as a point on the number line. So S is a set of points that are marked there in green. B in this picture is supposed to be both red and green. We might have some more red points to the right of B, maybe. So B is an upper bound. This is another way to think about it, maybe, that some people might prefer. So B is an upper bound for S. An upper bound for S. If no point, so thinking about it in kind of visual terms, in terms of the number line, if no point of S is to the right of B on the number line. So basically we have, B there, if there's no green point to the right of B, then B is an upper bound for the set of green points, which is the set that we're calling S. Okay, and of course, if that happens, then anything to the right of B will also be an upper bound for S. So basically, something is a number is an upper bound for a given set if it's greater than or equal to all the elements in that set. So visually, it has this kind of picture that if you're an upper bound for the set of green points, so for example, if you're that red point, it just means that there's no green point to your right on the number line. Okay, and of course, B here is colored both red and green, which means B is an upper bound for S. There's no element of S to the right of B. That's certainly true. And that particular B, which is that one, it's supposed to be both an upper bound for S and an element of S. It's colored both green and red. The fact that there's no green point to its right tells us that it's an upper bound for S, but also nothing to the left of B can be an upper bound for S because anything to the left of B will have green points to its right. So B there is kind of, amongst all the upper bounds for S, this particular B is kind of distinguished because it's the least upper bound. There's no more upper bounds to the right of it. Okay, so B is an upper bound for S if no point of S is to the right of B on the number line. And I think that's kind of a good way to think about upper bounds. If you prefer this kind of text-based description, that's absolutely fine as well. And of course, it says exactly the same thing. But if you're in any way kind of put off by the formality of that, and you prefer the kind of visual version, that's completely fine. So it just means that B is bigger than everything in S, basically. Okay, and then of course we also have the corresponding analogous concept of a lower bound. So an element B is an upper bound for S if nothing in S is to the right of B. An element C, or A, it's called in the note there, is a lower bound for S if there's no element of S to the left of A. So A itself may or may not belong to S in this case. It doesn't have to, but the point there is that there's no element of S to the left of A. So this and that pink color, I'll write it down. A, which is, there's one sort of suggestion for A there. Here's a few more things that are lower bounds for S. A is a lower bound for S if no element of S is to the left of A. In other words, A is less than or equal to every element of S. Okay, so if one thing is a lower bound for S, then everything to its left is also a lower bound for S. So that's the concept of an upper and lower bound. And I guess, I think the concept, I don't think is too involved, but the kind of language surrounding it and the notation that surrounds it can be a bit cumbersome. So I suppose my advice to you here is to kind of make friends with these words, upper bound and lower bound, and be sort of, to kind of give yourself some time to kind of just think about how these words are used and how these terms are used so that you're comfortable with the definitions. And if you have any trouble with that, just get in touch with me. Okay, that is the kind of setup for upper bounds and lower bounds. We've talked about bounded sets before, but I don't think we've particularly kind of concentrated on these notions of a number being an upper bound or a lower bound for a set. So that's fine. And of course, not all sets have upper and lower bounds. If you take the set of integers, it doesn't have any upper bounds because its elements extend indefinitely to the right. And if you take the set of integers, it doesn't have any lower bounds either because its elements extend also indefinitely in the negative direction. Okay, that is the ideas of an upper and lower bound. And here's just some more about the same thing. There's the same definition repeated. And S is bounded above if it has an upper bound. If it has any upper bounds, and if it has any, it'll have infinitely many, because if you have a particular upper bound for S, then all the elements greater than that will also be upper bounds. It's bounded below if it has a lower bound, and it's called bounded if it's bounded on both sides. Okay, so in this section, we're interested in sets that are bounded on at least one side. Otherwise, the concepts that we want to talk about don't arise. Okay, right. That's a lot of talk without actually saying what it is that we want to talk about. So here we go. So maximum and minimum elements mean what you'd expect them to mean. The maximum element of a set, if it exists, is just the greatest element in the set. Okay, so, and here again is kind of a probably overly fussy version of the same statement. If we have a subset of R and there's a number M that's both an element of the set and an upper bound for the set, then M is called the maximum element of S, or greatest element of S, and denoted max S. Okay, and so we can look at a couple of examples first. So, if you take the set whose elements are 1, 3, and 24, then the maximum element there is 24. It's just the greatest element in the set. If you take the closed interval from 0 to 1, that includes all real numbers that are at least equal to 0 and at most equal to 1, including both 0 and 1 themselves. That is 1. The greatest element there is 1. So 1 is a upper bound for that set because nothing in that set is to the right of 1 or is greater than 1. 1 is also an element of the set. Okay, so it's the maximum element. It's greater than any other element in the set. Okay, and if you take a set like the rational numbers, but that's not bounded, it has no maximum. But another example of a set of real numbers that has no maximum is the open interval from 0 to 1. Okay, so remember that includes all real numbers that are strictly between 0 and 1, not including 0 and 1 themselves. And this set has no maximum, even though it is bounded above and below. There's no greatest element there. You can say, well, 0.99999 is there, but there are greater elements than that there because you can put more nines at the end. Okay, the element 0.9999999 without terminating is actually equal to 1, so it's not there. So this set has no maximum element, even though it is bounded above, for example, by 1. So it's kind of like, in the open interval from 0 to 1, it's all, the number line, it's all the points between 0 and 1. But not including those two endpoints themselves. So this is 0, this is 1. And so kind of where the maximum element should be is this kind of hull. There's no, it's kind of missing. Okay, so we have this sort of slightly strange situation when you think about it, that we have sets that are bounded above, but don't actually have a greatest element. Okay, so and that's exactly the kind of issue that we're going to talk about. So that's what a maximum element is, and technically, so if there's a number m that is both an element and an upper bound for the set of S, then it's called the maximum element, denoted maximum of S. So, but a kind of more intuitively appealing way to say that would make sense to probably most of us, it would just be to say the maximum element of S is the greatest element of S. And if you use that as a definition, that's absolutely fine. If S has a greatest element, that's its maximum element. Okay. And similarly, if you look at the left-hand end of S instead of the right-hand end of S, so if there's a number that's both an element of S and a lower bound for S, then it's the minimum element, the least element, and it's denoted by min S. We'll look at the maximum. You can look at this from either side. We'll sort of concentrate on the maximum side for our examples. So a couple of remarks. A set can have at most one maximum element. And I guess that is a sort of sensible statement. If you look at it geometrically, the maximum element is the rightmost element. If there is a rightmost element, you can't have two of those. Okay, another way to say it, if you had two elements that were sort of candidates for being the maximum element of some set, well, then one of them would have to be less than the other one, and that one couldn't be the maximum element because the other one's greater than it. Okay, so yeah, and on the number line, the maximum element is the rightmost point. The minimum element is the leftmost point if such a point exists. Okay, so that's fine. I guess we can have this concept of maximum and minimum elements. Anybody have a comment or question about that? Okay, if not, then it still seems to, I still haven't sort of said what this key property of the real numbers is that we're supposed to be talking about. Okay, so there are two reasons why a subset of R might fail to have a maximum element. Okay, first, it might not be bounded above, and then it certainly won't have a maximum element, because if a set is not bounded above, then its elements persist indefinitely along the positive direction on the number line, and there's no way you could have a biggest one. They just, they just keep getting bigger without bound. So that's one reason why a subset might fail to have a maximum element. That's kind of not the one we're interested in right now, but that is certainly a reason. The set might not be bounded. And the second reason, which is a bit more interesting, is the set might be bounded above, but it might not contain an element that's an upper bound for itself. So it might not have a rightmost element, if you like. And here, if we take the open interval 0, 1, which is usually the go-to example for this phenomenon, although there are plenty of them, then this set is definitely bounded above because there's nothing in it that's greater than 1. So, there's certainly no element of this set to the right of 1. So this is the set of points on the number line that are strictly between 0 and 1. But if we take any element of that set, so take, so here's the picture, take an X here, wherever. Take an X that's kind of near to the right-hand end of it, wherever there's one already in there. So then X is a real number that's strictly greater than 0 and strictly less than 1. Okay. So no matter how near to 1 X is, on the real number line, there are more elements that are in between X and 1 because there's a gap between X and 1. It might be a really, really tiny gap, but it's a gap. And it contains more real numbers that are greater than X, which kind of defeats the idea that X could have been an upper bound for the interval 0, 1. So, so what we're saying here is that no element of that interval is an upper bound for the interval. We're not saying that the interval doesn't have upper bounds. We're saying that there's no real number which is simultaneously an element of this interval, which would mean it has to be strictly less than 1, and which is also an upper bound for this interval. Because if you take any element of that interval, it looks like this. There, no matter how close to 1 it is, you can zoom in, and there's a gap between it and 1. So to the right of it, there are more elements that still belong to the interval. And if you pick one of those and zoom in again, you can do the same thing. So there's no element. So this interval doesn't have a maximum element, although it is bounded. It's a very nice set in many ways. It's a connected piece of the real number line. It's just an interval of length 1, but it doesn't have a greatest element. You can travel to the right from 0 to 1, and you can pass all the elements, but there's no last one that you passed. Okay, there just isn't. No matter which one you look at that you passed, there are other ones to its right that you've passed after that, and there's no last one. Okay, even though it was when you passed the point 1 really that you had passed all of them, but still there was no last one. Okay, so this set doesn't have a maximum element, which is fine. Maybe it would be nice if it did have the greatest elements, but it doesn't. We have to live with that. Okay, so this open interval, although it's bounded, has no maximum element. It also has no minimum element because you have exactly the same situation at the other side, where you have 0 not belonging to the set, but everything to the left, to the right of 0 belonging to it. Okay, so an example of a subset that does have a maximum and a minimum element is a closed interval like 2, 3. So, if you look at that interval, 2 is here, 3 is here. The closed interval from 2 to 3 includes all the real numbers whose decimal representation starts with 2 point anything, and it also includes the number 3.0, which is the greatest element in there. So that particular set has its minimum element is 2, its maximum element is 3. There's really kind of no issue. It has a greatest element and a least element. But if you left out the 2 endpoints and took everything else, then you wouldn't have a minimum or a maximum element. And so remark is that every finite subset of the real numbers does have a maximum element and a minimum element. And I guess, well, as long as it's not the empty subset, but every non-empty finite subset does. Maybe I should be a pedant and write that. So, and the reason there, of course, is if you have a finite subset of the real numbers, maybe it has 20 elements, you can just list them in increasing order from the least one to the greatest one, and it has the smallest one and the greatest one. And another remark is that, maybe I'll just write this down too, if maybe we're thinking about is that every bounded subset of the integers has a maximum and a minimum element. Well, again, at least if it's not empty. And I guess there, the reason for that, I suppose, really is that just how different the geometry of the integers is from the geometry of the rational or real numbers, that the integers are spaced out. So if you have a bounded subset of Z, it has to have a leftmost element because the elements are spaced out. You can't have this thing of the elements sort of being crammed in near to some lower bound, but without that lower bound actually being included in the set, because the integers are sort of spaced out, if you're traveling from left to right and you've got a bounded subset of Z in mind, eventually you're going to meet an element of Z for the first time. You're not going to have sort of already skipped over loads of them before you sort of, before you can sort of pick out one that's there. So every bounded subset of Z has a minimum and a maximum element. If the bounds for the set if the set is bounded between those 2 points, there's a leftmost element and a rightmost one. You can't avoid that if you're talking about subsets of Z, because of the fact that the elements of Z are evenly spaced as opposed to being densely packed in to the number line. Okay, so the thing that's probably new here, because there probably hasn't been a whole lot used so far in what I've said, is probably the next bit. So for bounded subsets of the real numbers, there are these concepts called supremum and infimum that are closely related to maximum and minimum, but they're not the same thing. So basically, the way I think about this informally, so I can't really write this down, is, if you look at something like the open interval from 0 to 1, it doesn't have a maximum element. It doesn't have a greatest element. But the thing that sort of should be the greatest element of it is 1. Okay, it's just missing from the set. That set, the open interval from 0 to 1, it has a missing element where 1 should be. Okay, but everything to the left of that is included in the set. So we can't say that 1 is the maximum element of that set because 1 is not there, it's not in the set. But 1 is what they call the supremum of the set. Okay, so it's kind of the thing that it's sort of the thing that should be the maximum element of a bounded set. Okay, a set that's bounded above. It's the thing. It's the number that's in the place where the maximum either is or sort of would fit. Okay, and that's a intuitive kind of notion that isn't a precise definition, but I think it kind of makes sense to me when I think about it. To make that precise, as usual, of course, we need a form of words that sort of stands up to scrutiny better than the thing I just said. And here it is. So this is the famous axiom of completeness for the real numbers. Okay, so to give a kind of detailed proof of this, you'd have to give a more elaborate construction of the real numbers than what we've done in this course. So we're not going to do that, but what the axiom of completeness says is, if we have a subset of the real numbers that's bounded above, then it's got upper bounds, Okay, so we've a subset of the real numbers that's bounded above. So let me imagine that its points are colored green. So maybe it consists of a few separate intervals and some scattered points, something like that. All these things live on the real number line. Oops. So the green points are the ones that belong to S. Actually, let me start this again. We have a number line, and we have a set S in mind. S is maybe colored green. It has some various points, but S is bounded above, and that means that there's a point beyond which the elements of S don't go. So here's such a point, let's say. And if that's an upper bound for S, then so are all these points to its right. Okay, so all these points that are colored red are upper bounds for S. If you have one upper bound, then everything to the right of that is also an upper bound for S. And so the S here are the points that are colored in green. This is really a terrible picture. I'm sorry for that. Okay, so the assertion is that if you look at the set of all upper bounds for S, so these points that are colored red, so associated to any set that's bounded above, you have the set of all its upper bounds. Anything that's an upper bound for S goes into this set. Okay, so an element is in the set of all upper bounds for S if there are no green points to its right. Okay, and the assertion is that that set will always have a minimum element. Okay, the set of all upper bounds for S always has a least element if S is bounded above. That least element might or might not belong to S, depending on whether S has a maximum element or not. But the set of upper bounds for S, which are written here in red, always has a minimum element. That number is called the greatest upper bound, the least upper bound for S, or it's also called the supremum of S. Okay, so the word supremum, I suppose, captures linguistically captures the idea that we're talking about sort of the biggest thing in S. Supremum is also called the least upper bound, which is a kind of completely explicit name, I suppose, because we can sort of you can see from the name there exactly what it means. Amongst all the upper bounds, it's the smallest one. And we also have the corresponding notion on the other side that if a set is bounded below, then it's got a bunch of lower bounds, which are points that have nothing in S to the left of them. The set of all lower bounds has a maximum element, which is essentially where the minimum element of S either is or would belong. And that is called the infimum of S, and it's denoted INF for inf. The infimum is also called the greatest lower bound. Okay? So the axiom of completeness for the real numbers tells us that every subset of S that's bounded above has a least upper bound, that amongst all its upper bounds, there's at least one. Okay, and that is called the supremum of S, or it's also called just the least upper bound. And same on the other side, that if you have a set that's bounded below, then it's got a bunch of lower bounds, and amongst all those, there's a greatest one, and that's the greatest lower bound of S. Okay, so fine, but now, great, we've said that, and that is, we can take that on board, I guess, and incorporate it into our kind of working knowledge. I suppose thinking about it in terms of examples, like if we went back to that sequence of rational numbers that was approaching pi, we had 3, 3.1, 3.14, and so on, like successive truncations of the decimal representation of pi. The set of all those things is a set of rational numbers, okay, that are all sort of clustered around, clustered between sort of 3.1 and 3.15, let's say. So that it's certainly a bounded set. And it doesn't have a maximum element because it's kind of increasing all the way. Every extra decimal digit that you add on at the end makes this thing a tiny bit bigger, unless it's 0, in which case the next one that isn't 0 will make it a tiny bit bigger. So that's a set of rational numbers that doesn't have a maximum element, because this process of adding on the extra decimal digit goes on forever. And even though the increases are tiny, tiny, tiny as you go out, they're still there. So supremum of that set, the least upper bound for it, would be like the infinite decimal representation of pi. So it would be pi, which is not itself a rational number and doesn't itself belong to this set of truncated decimal representations of pi. So that's kind of another kind of instance of the same concept, I guess. Okay, and I suppose the last thing that I really want to say today is that in order to kind of get a sense of why this concept is so important for the real numbers and why it really sort of captures something about the real numbers, we can observe that it's not shared by the rational numbers. So, okay, what are we saying here? Just to be clear on this, because it is a point of a sort of very precise point. We're saying that if we have a subset of the real numbers that's bounded above, then it has a least upper bound. Amongst all its real numbers that are upper bounds, there's the smallest one. Okay, so we're taking a subset of real numbers and saying that there's a real number which is its least upper bound. So to kind of try to persuade you that this is something worth fussing about, worth being interested in, I wanted to try to argue that the same would not be true if we replaced the real numbers with the rational numbers, and that's sort of the last example. Okay, so the claim is that this axiom of completeness, as we've stated it for the real numbers, wouldn't hold if we replaced the real numbers with the rational numbers. Okay, so if we take a set of rational numbers that's bounded above, okay, so what I mean here by saying that this doesn't hold for the rational numbers is that if we take a set of rational numbers that's bounded above, rational numbers that's bounded above, so it has upper bounds. Okay, well, obviously it's a set of real numbers if it's a set of rational numbers, so it does have a supremum that's a real number, but the claim is that it need not have a supremum that's a rational number. It need not have a least upper bound that's itself a rational number. Okay, so it'll have a least upper bound in the real numbers if the axiom of completeness is true there, but it need not have one that's a rational number. And so this, I hope, kind of, when you have a chance to think about it, might give some justification to the use of the term completeness here. What we're trying to say here is really the real numbers are the things that you need to ensure that every set of rational numbers that's bounded above will have a supremum. You know, to introduce a supremum for every set of rational numbers, you can't do it just within the rational numbers. They just don't exist there. You have to introduce the real numbers. So the real numbers is some kind of more complete version of the rational numbers, where every bounded set has a greatest lower bound and the least upper bound. Okay, so to make that point, or to try to argue it, let's look at this particular set of rational numbers. So we're talking about the set of rational numbers whose square is less than 2. Okay, so that's fine, that we can talk about that. It includes both positive and negative rational numbers, but it's bounded because, for example, it doesn't include anything greater than 3, and it doesn't include anything less than -3, because if you're greater than 3, your square is definitely not less than 2, and if you're less than -3, your square is definitely not less than 2. So this set is certainly bounded. Okay, so S is the set of rational numbers whose square is less than 2. So it includes things like 0, 1, 1.1, you know, 5/4 is there because its square is 25/16, it's less than 2, and so on, things like that. Okay, S consists of all those rational numbers whose square is less than 2, it's bounded above, for example, by 2 or by 3 or whatever. And the positive elements of S are all the positive rational numbers that are less than the positive number square root of 2, which is not rational. Okay, and the assertion is that S doesn't have a least upper bound in the set of rational numbers. Okay, so and to see this, supposing that we have some rational number, we're on the number line, we're thinking only about rational numbers, we're kind of pretending that we don't have any real numbers. So there are any irrational numbers. So suppose that we have some x in mind that's a candidate for being the least upper bound of S in the real numbers. Okay, so we have elements of S that are rational numbers whose square is less than 2. Okay, so x, when we square it, its square is going to be either less than 2 or greater than 2. And remember that x is like a candidate for being the least upper bound of S in R. So if x squared is less than 2, 2 is over here somewhere. So if x squared is less than 2, x squared can't be equal to 2 because x is a rational number and 2 is not the square of a rational number. Okay, so that's a sort of key point to observe here. X squared is definitely not equal to 2 since no rational number has square equal to 2. So the possibilities are that x is either less than 2, x squared is either less than 2 or greater than 2. If x squared is less than 2, then on the number line, there's a gap between x squared and 2. And in there are more rational numbers. So pardon me. If x squared is less than 2, there's a gap in the number line between x and the square root of 2, which I'll put in a different color because it's not rational. Okay. Try that again. So x is here. If x squared is less than 2, then x is less than the square root of 2. That means there's a gap in the number line between x and the square root of 2. And in that gap are more rational numbers that are greater than x, but still less than the square root of 2. So still elements of s. So in that case, x can't be an upper bound for s. It certainly can't be the least upper bound for s. Okay, so if x is a rational number, which we are postulating might be a least upper bound for the set s, and if x squared is less than 2, then x on the number line is less than the real number, the square root of 2. There's a gap between x and the square root of 2 there. And in that gap, we can insert more rational numbers whose square is still less than 2 and which are better candidates than x, in a way, for being the least upper bound. And to show that x is not an upper bound for s, because there are elements of s still to its right. On the other hand, if x squared is greater than 2, that means that x is to the right of the square root of 2 on the number line. So the second case is that we have some element x out here, which is a candidate for being a least upper bound for s. If x squared is greater than 2, that means that x is greater than x is to the right of the square root of 2, and there's a gap in the number line then between the square root of 2 and x, in which are more rational numbers that also are upper bounds for s, but which are less than this x. So x can't be the least upper bound for s, because if its square is greater than 2, there are other better candidates. There are other upper bounds for s to its left. If its square is less than 2, then there are other elements of s to its right. So it's not an upper bound for s. Okay, so basically the kind of issue is that the least upper bound for s is really, it's the square root of 2. That's where it is, and it's not a rational number. Okay, so there's no rational number amongst all the rational upper bounds for s. There are plenty of them, but there's no smallest one. You can make them as near as you want to the square root of 2, but the square root of 2 itself is not a rational number. So if you're only working with rational numbers, then you'd say, well, this set doesn't have a least upper bound. There's no rational number with that property. Okay, so the point here is that the rational numbers don't have this completeness property that the real numbers have. Okay, in order for this particular set S to have a supremum, we need to have a number system where the square root of 2 is recognized as a number. So we need to have the real numbers. Okay, so, and the same issue on the other side, the infimum of S in R is the negative square root of 2. So the point of this example, which I hope is worth giving a bit of thought to, is the axiom of completeness doesn't hold for the rational numbers. A bounded subset of the rational numbers need not have a supremum or an infimum that's itself a rational number, but it'll have one. It'll have both an infimum and a supremum instead of real numbers. So, sorry, I have gone on too long. That is basically the content of this section. So I guess the things that are important in it are the concepts of supremum and infimum, the distinction between supremum and maximum, and between infimum and minimum. If a set has a maximum, the maximum will also be its supremum, but a set that doesn't have a maximum can still have a supremum. And so tomorrow what we'll do is we'll have a bit of a recap about chapter 2. We'll have a bit of general advice about the format and style and nature of the exam question in relation to chapter 2 and how one might go about answering it. And we'll have a look ahead to chapter 3 as well. So I'm going to leave it there. I'm going to stop the recording now. Thank you very much to everyone who's joined us for the recording, and see you tomorrow.